Welcome to this video on stochastic cash flow modeling. We're going to go through the list of activities that the video states that is going to go through. So we'll start by updating the loan schedule worksheet to allow for a different interest rate at the end of each year. So here's our week 1 video, which is where we're going to start from, and I want to allow this cell here to be different every year. The logical way of doing that is to add a new column, which we'll call interest rate, and have a separate interest rate each year within the cash flow model. I'll fix up this formatting here so it's not like that anymore. And this can just be 20%. I'll make it 20% for all of these for the moment so I can be consistent with the rest of the model. And the interest due, rather than being linked to cell B1 here, I want to link to the appropriate interest rate in that year. Okay, so that's all good. And I've linked this to the interest due. Now the second thing that we're being asked to do is to make the payment required at the end of each year be equal to the payment required to pay the loan off if the interest rate was to stay constant. So in other words, this payment here at time 1 is the amount that I would have to pay off at time 1, 2 and 3 if this 20 was to stay the same each year going forward. So essentially what we're doing is we're going to use something very similar to this formula here, and I'm actually going to copy this in a moment, but we want the interest rate in this formula to reflect the interest rate in the time the payment's being made, and we want the time remaining in the loan to reflect the number of repayments still should be made. So let's copy this formula now. So I've just copied the text. I'll overwrite this and paste, so Control V. Now what I want to do is I want to update everything that reflects to interest rate, the B1, I want to be C7 here, and that can change as I copy down, so I don't need any dollar signs. So B1 there can be C7, B1 there can be C7, and that's perfectly fine. Now what I want to do is I want to change this time frame here, which is 3 years in the initial calculation. I want it to be based on the number of payments left in the year that it's calculated. So let's change this 3 here to be equal to, this is the maximum here, cell A9. I'm going to put an open bracket around this. Then I want to subtract the number of payments that have already been made, which here is 0. So at the time of the first payment, I've still got 3 payments to make. So A9 minus A6, I'll put $1 next to the 9 because I don't want that to change as I copy it down. I do want this to change as I copy it down. And so now this will pay off an amount as required to pay the loan off in 3 years in the cell that I'm working in now. I'm going to copy and paste what I've just put in here and also put it in where that 3 is because I need to do exactly the same thing there. And now I should have a formula that works for that particular year, and you'll see it's exactly the same amount. Now if I haven't made any mistakes, I can see one thing I need to do here. I need to put a dollar sign on that loan amount. In fact, I don't need to put a dollar sign. What I need to do is I need to make that reflect the outstanding balance at the start of the period. So this calculation here is the amount required to pay the loan outstanding at the start of the year off. So here I link it to F6. I do want that to change to F7, so I don't put any dollar signs or anything like that, and this will just copy down and work nicely. Okay, the rest of it I think is fine. So if I copy and paste this down, I get different numbers. I've obviously made a mistake somewhere. Let's see if we can establish where that is. So if C80, that's fine. F7 is correct. On A9 minus A7 is fine as well. B3, I didn't put, I need to change this to F6 as well. It's a bit silly, so let's change that to F6, and I think we might be in business now. There we go, we've now got the correct repayment amounts each year. And what's really, really nice about it is I can use different interest rates and the repayments will change automatically. So let's put just an 8% in here, for example. You'll see that the repayment amount changes, the outstanding balance changes, but the repayment at time 3 is automatically updated to allow for that. If I make this 6%, for example, we're still paying everything off here at the end of time 3. So I've now got a flexible loan schedule that allows different interest rates at each period. I don't need this interest rate anymore. I don't need this repayment rate anymore. They're all being calculated here and here. So I can delete that and that. I still do need a loan amount of $1,000. But what I might actually do to get that away from the inputs up here, I might make that something I put here instead. I might make this 1,000 and make this highlighted yellow. So I can put the initial outstanding balance there, and now I don't need any of these other inputs anymore. I will need them in a moment, but for something different altogether. Okay, so now I've got a cash flow model that works for different interest rates at different time periods. I've checked to see that it works by typing in different interest rates here. I'm now ready to make this loan schedule stochastic. In other words, making these interest rates random rather than fixed. Now, in the question, I've been told that the interest rate is independent and identically distributed with a mean of 8% and a standard deviation of 2%. Let's pop that here. So interest rate mean, interest rate standard deviation, and I'll make this a bit wider so we can put these numbers here. So 8%, 2%, and we'll highlight them yellow to denote the fact that they're inputs. I don't need this here either. Okay, what I now want to do is make these random numbers from this normal distribution. Now the first thing I'm going to do is show you how to generate random numbers in Excel, and I'm going to pop these over here in column H. So random number. I'll create 3 random numbers for the 3 years. And if I type in this function here, equals RAND, open brackets, close brackets, this will generate for me a uniform random number between 0 and 1. And in fact, every time I perform a calculation in Excel, that number will update. So it's new now. If I do that again, just left click here, press return, and new again. Okay, I'm going to copy this down, and I'll now have 3 different random numbers. The notes for this week of material talk a little bit about how these random numbers are generated, but it's not that important for the purpose of this video. So this is a uniform random number between 0 and 1. So actually what we can do is think of that as being from a cumulative density function, because that's what a cumulative density function is. It's a value between 0 and 1, and then convert that to this value from the normal distribution with mean 8% and standard deviation 2%. And there is a function in Excel that will do that for us. We'll convert a cumulative density value into a value from the distribution itself. And the function we want is norm.inv. Older versions of Excel might not have the full stop in the middle. We open the brackets and we'll see that there are 3 arguments to this function: probability, mean, and standard deviation. So the probability is the cumulative density value, this value here. The mean is the mean of the distribution. The standard deviation is the standard deviation of the distribution. Close brackets. I'll put a $sign here next to the 2 and next to the 3 because I don't want them to change. I do want the H7 to change when I copy this formula down. So let's have a look at this now, and I might make 1 decimal place here. We've got a random number of 0.792, which is the cumulative density value from here, the normal distribution with mean 8 and standard deviation 2%. So we would expect this random number to be above the mean, because if this was 0.5, and I can show you that, if this was 0.5, then the interest rate is exactly equal to the mean, because it's actually the median, and the mean and the median is the same for the normal distribution. I'll undo that by holding Control Z. The random numbers change again. Now we've got a random number very close to 0, which means that it's below the median, and so the interest rate is going to be below the mean and median of the normal distribution, which we can see that it is. This is also, let's copy this down now. This 0.55 is pretty close to the median, hence the 8.3% is just above the 8. And so you can see the relationship here between the random number and the interest rate. Now, having this change all the time gets a little bit painful. So one way I can get around that is to highlight all of these cells, then copy and paste values, this thing here. What I now have is some random numbers that are hard-coded. They're not going to keep changing every time I change something in Excel. So it can be quite nice for us to deal with if we're wanting to change some other stuff if we don't want the random numbers to change. Okay, we've been asked to perform 1,000 simulations and then do a few other things in the material for this video. We have been asked to look at the total interest due, which I can calculate here quite easily, equals sum of this thing here, which will make nice and orange. And I'll write here total interest, make that bold. Okay, so we've been asked to look at the total interest due. We've also been asked to look at the 25th, 50th and 75th percentiles of the total interest due. That's good. We also need to know some things about the interest rates in the first and second years as well for some of the probability calculations we're required to do later on in the question. So we're going to pull that information from here. Now we've been asked to perform 1,000 simulations. So what that means is we need 1,000 different versions of these random numbers. Now I'm going to pre-create these using method 1 from the documentation for this week. So I'm going to create a new worksheet, which I'll drag across to here, and I'll call this random numbers. Let's make it a bit bigger so you can see. And this is going to store all the random numbers I'm going to use for this exercise. So this will be simulation year. So the year is just 1, 2, 3 because that's the number of years I'm performing a single simulation for. I need 1,000 simulations, so I'll go 1, 2, highlight these two and drag it all the way down. So we keep dragging down till we've got 1,000 simulations. There we go. And let's create all of these random numbers. So I just go equals rand, open brackets, close brackets. These are still uniform between 0 and 1. Copy that formula across, double click on this and it'll go all the way down to 1,000. And so I've got all these random numbers that will change every single time I change this. And in fact, what I want to do, because I don't want that to happen, it's going to make my workbook very slow, is I'm going to highlight this. So if I highlight those cells like that and then press Control Shift down, it will highlight everything. I copy and then I paste the value. Now what I'm actually going to do is use some other random numbers that are going to be used from the video for this week's material. So this is off screen, you won't be able to see it, but I'm going to copy and paste a different set of random numbers, which I'm going to bring across here now. I've just pasted them with Control V. Now the reason I'm doing this is so I've got exactly the same random numbers as the Excel file for this week has on Wattle. You'll see exactly the same results rather than seeing something different because of different random numbers. But these are all the random numbers I'm going to use for simulation and for each year in that simulation. What I want to do now is I want to create a simulation input, which I'll call 1 for the moment. Then I'm going to link these random numbers here to that simulation, and therefore this will change automatically as well. I'm going to use a lookup function to do that. So equals lookup. I want to look for simulation 1. I want to look for it in this vector here. And the output that I want is from year 1. So it's this thing. Just here. Okay, that should give me the correct random number. I can look at this just to make sure. Yep, 0.324929, which is exactly what I want. Let's put some dollar signs here. In fact, I'm not even going to put dollar signs because I can't really drag this down anyway because the years go horizontally. So what I might do instead is I might copy this. This is the text, paste it, and I know all I need to do is change this to column C, and that will give me the second year reference. Then I can change this to column D, and it will give me third year reference. Okay, I can look at these random numbers here and see that they are consistent with these numbers here. If I change this to 2, then this here will be consistent with this here. So I've now got a nice little identity variable, as it were, that I can literally change this and the rest of this will all completely change. Pardon me. So now what I want to do is actually run these simulations. And the way to do that is very similar to what we did back in week 1 when we were looking at the effective interest rates. We're going to run a macro that's literally just going to change this simulation number here, copy and paste the information that we're interested in, and then rerun with a new simulation number. We'll put it in here, although to be perfectly honest, this is fairly useless to us now, and we'll call this results. So let's start by structuring what we want to get out of this thing. So we'll start with simulation. In fact, I might literally just copy that from here and paste it. I don't need the year bit. So this is going to have the output that I want. Now the way I'm going to do this, it might look a little bit strange, but it'll make sense when I actually write the macro. I'm going to put for any given simulation that we're working with, let's just call this 1 for the moment. This will be interest rate 1, interest rate 2. Excel generally is smart enough to know actually if I copy this across it will change it automatically to interest rate 3. And then total interest due. Okay, this is equal to this thing here. Let's make it a percentage with 1 decimal place. This is equal to this thing here. This is equal to this thing here. And this is equal to this thing here. Let's make these all percentages. None of these really need to be bold. And these are all outputs. Now, what I'm going to do is I'm going to copy and paste this down into its relevant row every time I've run one of the simulation iterations. Now, in order to make things even nicer, what I'm going to do is link the simulation change to this cell here rather than this cell. So what I'll do is I'll say this is equal to this number here. And now when I change this to 100, for example, these are all now linked to the new random numbers that are sitting over here. I actually don't even need to touch loan schedule. I can just use this and copy and paste it down into here for the relevant simulation numbers. So now I'm ready to start thinking about running some simulations. So let's do that now. We need to have a look at the macros. So we'll edit this one here, which you can see on screen now. So this is our original with interest effect worksheet. We'll now activate results instead. I want to change this number here. I want to go from I equals 1 to 1,000. And I want to iterate results A2 is equal to I. That is now going to change this simulation number here every time I run through the simulations. I actually don't need 2 rows here. I can get rid of this. I can go results. Now I want to copy this thing here down into its relevant row. So I want to, the left hand side of this is what I am pasting to. So I want this to be linked to columns B to E, which is columns 2 to 5. And I want it to be pasted in row 4 to start with, which means it's I plus 3. Okay, there we go. So that's now the correct reference for where we're pasting to. Now, this now needs to be results as well. And I want this to be B2 to B5, to E2. That is where I am copying from. And now this macro should work for us very nicely. So let's play it and see if it runs. Okay, we get an error here. Let's have a look and see if we can debug it. It says subscript out of range. It's because I've typed result. It should be results instead. So let's stop the macro now. So it has to go right back to the start, and we press play. I can see that it seems to be working okay. It's relatively slow. We'll skip forward in the rest of the video to when this is finished. Okay, we're just about done now. It is running very, very slowly. You'll find that on the ANU lab computers it runs a lot faster. I'm not sure why it runs so slowly on my computer. Anyway, we now have a whole bunch of results in some fairly nasty formatting. So for these ones, I'll change them all to be percentages with 1 decimal place there. The total interest due is fine. There's a couple of extra things that we want to do here. The first thing we want to do, well, we've been asked to run a histogram and an empirical cumulative density plot on the total interest due. I'm going to do that last in the video. First thing I'm going to do is calculate the 25th, 50th and 75th percentiles of the total interest due. So really what we've got here is 1,000 observations from the distribution of total interest due. We don't know what the distribution of total interest due is. We've just got this sample. Now, in order to estimate the percentiles of the distribution of this, we just use as our estimate the percentiles from the sample, which makes sense. So our estimate of the 25th percentile of this thing here is just the 25th percentile of the sample. So let's insert a few rows here, which is going to give us some horrible formatting. I'll get rid of that because I'll keep the other one for a moment. Let's calculate 0.25 percentile, copy and paste this, make this 0.5, whoops, wrong place, 0.5, 0.75. Okay, so the percentile can be quite easily calculated through Excel. There is a percentile function. So percentile, open up the brackets, the array is this thing here, which I know goes down to 1006 because there's 1,000 observations. And the percentile that I want to calculate, which is K, is this thing here. I'll put some dollar signs next to the array because I don't want that to change. I do want the C to change. And we'll end up with these values here as the 25th, 50th and 75th percentiles, which you can compare to, well, this is the value for the 1,000th simulation. You can see that it looks relatively symmetrical. There's a difference of about $16 here and about 17 and a little bit dollars between 25 to 5 and 5 to 75. So we'll see that more when we look at the histogram a little bit later. But we've now performed the percentile calculations that we're required to perform. Now what I want to do is something a little bit different, and that's to add a macro button. When you are running macros, it's often nice to be able to just press a button rather than having to go into the macro code and press play all the time. So I'm going to insert 3 rows here, and the button I can get by going to Developer, Insert, Form Controls. This thing here is going to be my button, and I just draw it, left click, hold, and then I can assign a macro to it. The macro I'm going to assign is this macro 1 here, and OK. What that means is if I left click on here, that macro is going to run. I'm going to edit the text and call this run simulations. Now I know that if I click on this button here, it's going to run the simulations. Now, one thing I've got to be careful about is because I've changed the structure of this worksheet, the macro runs along these cells here, whereas it was running a little bit higher before. So I actually need to go into the macro and just change it. It's just sitting in here behind. Let's pull it up. So this now is not row, I'm not starting at row 4, I'm starting at row 10. So I want this to be I plus 9. The columns haven't changed at all, and I want this to be row 5, which is where I'm copying from. You can see row 5 just there. And then I also need to change where the value here for the simulation number is being updated to make sure it refers to row 5 as well. And now I'm done, and I can go back here and run the simulations. And you can see that it's all working quite nicely. If you were a little bit attentive there, you'll notice that there was a bit of an error that I cut out of the video where I incorrectly forgot to change cell A5 here. It was cell A2 and it was all working very badly, so you would have seen a whole bunch of numbers that looked exactly the same. We're running a bit faster now, which is good. So we've now run that, got exactly the same numbers that we had before, and we've now got this button that we can use to run simulations anytime we want to run the simulations. Now, this thing I want to do is calculate the probability that the total interest due will exceed $180. Now, any form of probability we want to calculate is pretty simple. Really, all it is calculating the number of observations that meet the criteria divided by the total number of observations. I'll write it down here. So number of observations meeting criteria divided by total number of observations. So we're looking for the probability that the total interest due will exceed $180. We know that this thing here is 1,000. We just need to count the number of observations that have a probability of, the number of observations that have total interest due greater than $180. And that will give us our estimate of the probability just by using the sample. So let's perform that here now. So we're going to slide it in just here, I think. Probability interest is greater than $180. Okay, we know that's equal to the total number of observations greater than $180 interest due divided by the total number of observations. So it's equal to, we can use a COUNTIF function here, which you may not have seen before. So COUNTIF will count the number of observations in a range that meet a certain criteria. So we go from here, E10 down to E1009. The criteria is, and we always put this in quotation marks, greater than 180. If I just have a look at this cell now, I can see that 237 observations meet that criteria. I need to divide that by a count of the total number of observations in here, which I know is going to be 1,000, but I'll use a count anyway. And that gives me 0.237. So that's my correct now probability calculation to meet that component of the question. And there's actually something else I want to show you here. I want to show you how this number changes as you add more and more simulations. Pardon me. So what I'm going to do is I'm going to calculate this down here as the cumulative value of this for each number of up to that number of simulations. So here is going to be the probability that the interest due is greater than $180 just for simulation, across simulation 1, then with simulation 1 and 2. So we're going to adding one new observation every single time. So I can repurpose this thing here. Now what I want to do is I want to count from E10 to E10, same thing here. Then I'm going to put a $sign in front of just the first E10 here. And what that's going to mean is that in this second value here, I'll now be doing the COUNTIF across 2 cells and 2 cells there. So basically I'll just be recalculating this probability, adding one new observation in every single time. This is relevant to the conversation on convergence that you will have seen in the notes for this week. We can see how this probability changes over time and whether it stabilizes. Now, this is not something you need to worry about for assignment 2 in this course, but it's just interesting to see how this changes. Let's make this just 3 decimal places. There we go. And then let's just draw a little table here showing number of simulations, and we'll go from, say, 100, 200 down to 1,000. And we'll see how that probability changes. The solution file for this week's material will have a little bit more information in the headings, but you can follow on quite easily in the video without too many problems. So this probability here I want to be based on the first 100 simulations only, on the first 200 simulations, on the first 300. I can use a lookup function to do that. So look up this value here. In here, I know that goes to 1009, so I don't have to keep dragging it all the way down. And I want to pull this number up here. It also goes to 1009. and I don't want any of these to change. Okay, so 0.24, let's copy this down. Again, we'll use 3 decimal places. So we'll see in the first 1,000 simulations, the first 100, the probability is 0.24%. Across a whole 1,000, it's 0.237. So it increases a bit, decreases. Now, the idea of convergence is really dependent upon the purpose of the question being answered. So I'm not going to comment here about whether this is converged or not, because it depends on how exact you need the answer to be. But you can see how 100 simulations doesn't give you that big a difference to 1,000. And in fact, the first 500 simulations have a probability of about 0.256, which must mean that the second 500 have a probability of about 2.1 in order to make the average between this and 2.1 equal to 0.237 over the entire 1,000. So you can see that the number of simulations you use does have a pretty big impact on the result. Not something you need to worry about for this course. You can always just use 1,000, but it is something I wanted to show you. Okay, some other questions we want to do before trying to do this histogram. We want to have a look at some conditional probabilities. So we're being asked for simulations where the total interest due is lower than $140, the probability that the interest rate in the first year is less than 7%, the interest rate in the second year is less than 7%, and the interest rate in both the first and second years is less than 7%. Let's have a go at doing that now. We'll pop it over here. So I'll say where total interest is less than $140, and we'll go prob int rate 1 is less than 7%. Note that the average interest rate is 8%, so we're looking at the lower tail, or the lower half, of the distribution here. Probably that interest rate 2 is less than 7%. Now we know that overall that probability is going to be less than 50% because the average interest rate is 8%. Let's see what we get in this instance. Prob int rate 1 and 2 is less than 7%. Okay, now in order to do this we need to revise our conditional probability rules. Now remember that the conditional probability rules are that the probability of B given A is equal to probability of A and B divided by probability of A. So let's imagine now that A is this thing up here, which I'll copy and paste. B is basically this row up here. I'll just use this as an example to start with, and then we'll change as we need to. So this calculation here, given this events, will give us this thing. We'll put it over here, obviously. So we want the probability of A and B divided by the probability of A. Now, both of these probabilities, A and B, and then probability of A, are going to be divided by 1,000 because that's the total number of observations. So in fact, what we can express this is in this instance is equal to number of A and B divided by number of A. And let's do this. So the number of both this and this, we can use a count ifs function, and it works exactly the same way as a count if, but we can have multiple criteria, and it will only count where all of those criteria are met. So the first criteria is that this needs to be less than 140. Oop, don't close that off. Second criteria is that this needs to be less than 7%. So now we've got a total of 151 observations that meet both of that criteria. We then divide that by, and what I'm going to do is I'm going to be a bit lazy and copy this formula, but I'm just going to remove the criteria that I don't need, which is the criteria of the probability of interest rate 1 being less than 7. this thing here, count ifs works perfectly fine if you've only got one criteria, except when you made a mistake. Oops, I don't want to accept that. I've accidentally deleted one of those quotation marks. Okay, well now we've got a result of about 79.1%. So the probability that the interest rate is less than 7% where the total interest is less than $140 is 79.1%. Let's do the same thing here. This is really easy. We just copy this formula. I'm not going to try and design it in a way that I can copy and paste it down. And I change this here to be C rather than B, because now I want to refer to interest rate too. And that result is 70.2%. We'll try and actually no. Let's try and understand these results now before we move on. So we know that the probability that the interest rate is less than 7% is less than 50%, because this is below average. But when the total interest due is less than 140, that probability jumps up really high. And that's because this $140 is very low compared to, well, the 25th percentile there is 145. So we know that in order to get that total interest due to be that low, we need low interest rates for that to occur. Now, why are these numbers different to each other? Have a think about that for a moment. Why is this probability less than this probability? Well, the answer is that the interest rate one has a bigger impact on the total interest due because it's applying to a greater loan amount. Interest rate one applies to this outstanding balance, whereas interest rate two only applies to this. So these values have the value for interest rate one has a bigger impact, and so therefore the probability is higher that it has an interest rate of less than 7% than it is here. Now this value we can again copy from here. We need an extra element in the count ifs function because we need both interest rate 1 and interest rate 2 to be less than 7%. So we'll just copy that, paste it, put a comma there, and make this B. So now we've got all the criteria that we need, and we'll see that the result is about 50.8%. So it turns out in order to get total interest due less than $140, it's not really necessary for both interest rate 1 and 2 to be less than 7%. It's one or the other is usually sufficient, and particularly interest rate 1 is enough. So now we've completed that part of the question. The last thing we need to do is to do a histogram of the total interest due. And I've left this to last because it's a little bit tricky in some aspects. Now Excel does do histograms. It doesn't do them very well. So let's now have a look at what Excel does when you try and do a histogram. In order to make it work, you need to have the analysis tool pack downloaded, or at least actioned. So if you go to Options, Add-ins, and then Go here, you'll see what add-ins you've currently got installed. I've already got the analysis tool pack installed. If you don't, you'll need to make sure this is clicked here. Otherwise you won't be able to do this. You also won't be able to do regression, which you'll need to do later in the course. Okay, now we find the histogram here in Data Analysis, and there it is there. Now Excel will ask you what the input range is, and that's the collection of observations, which is this thing here. Bin range we'll have a look at in a moment. Labels, I can't really remember what that does, to be perfectly honest. This is where output options is where you say where you want it to go. I'm going to plonk it right here, I think. I will tick labels and we'll find out what it does in a moment. I'll also tick cumulative percentage. I'll also tick chart output, and we'll see what they do in a moment. Okay. So here's what Excel outputs, and I've just moved this down here so we can see it a little bit better. The first thing to note about what Excel does is that the bins that it selects are absolutely horrendous. So they have weird and wonderful decimal places. I don't know how Excel actually does this, but you clearly want to use round bin numbers to get sensible, interpretable results. This count here is the count of the number between it'll make sense if I explain it here. It's the count of the number between this and this. This number here is the number below this. This is the number above this. This is the number between here and here, and then you've got a cumulative density amount as well. Now let's fix these bin numbers because they're quite frankly horrific, and the bin numbers that I'm going to use bin numbers that are 10 wide. Now these are hard coded, there's no formula here, so at the moment I'm just going to delete this, and I'll go from 80 up to, how hard does this go? 230, so I'll do something similar. Let's go to 230, delete the rest of this, and now I've created my own bins. Now you can use these. If I now go to data analysis, histogram again, that doesn't change, but now I've got the option of choosing the bin range that I want to use, which is going to make everything look a huge amount nicer. I'll leave everything else the same and let's see what Excel comes up with. It will overwrite the existing data, that's not a problem. I'm happy to overwrite that. A histogram bin range and output range overlap. I don't know what that means. Oh, that's because it's not going to let me copy my output straight over the top of it. So let's put the output range here instead, so it copies it there. Let's try that. Okay, that's my old one. Let's get rid of it. Let's get rid of this as well. Okay. Now, for some reason, Excel has not used this as the first bin. I'm not really 100% sure why that is the case, but you can see that at least these numbers here look much nicer than they did before. Let's delete that, and this is the number below 90. If you really wanted to do your own histogram and not let Excel do it for you, then you actually can quite easily just create your own bins and then do a whole bunch of calculations using countif functions, and it will perfectly work for you. Cumulative density is quite easy to calculate as well, obviously. So here's a histogram which also looks absolutely terrible. Let's make it a little bit bigger to start with. Frequency is probably okay on that axis. Let's now make this total. Actually, what we might do is we might go less than dollars, and we might change this thing here to be total interest across 1,000 simulations. Okay, I'll move this inside because there's really no need for that to be there. I'll do a couple of little tidying things here. Firstly, there's no reason for this to go above 100%. So that can just be 1. We can see now our cumulative density line. Our histogram itself looks relatively symmetrical, which is interesting. It tells us the data is pretty close to normal. If we want to confirm that this is actually correct, we can also go back up here and look at these percentiles and make sure they match up with the cumulative density line. So the 25th percentile, $145, should be consistent with around about here, which it looks like it is. So that is how you do a histogram in Excel. You are going to have to fiddle around with it yourself and create your own bins because it gives you horrendous output if you don't. Now that brings me to a close for the video. I hope you found this interesting and useful in preparing you for doing stochastic cash flow modeling. We'll do some more examples in class as well, but for now I'll farewell.